All right, tonight's presentation is from Lenny LaBelle. He is based in New York City and is a CTO and co-founder of Sleek Technologies. He is also a Microsoft MVP on the data platform. And rather than having you read all this long text, I'm just going to turn it right over to Lenny.
Good, thanks, Chris. Don't read that. Yes, there we go. Hi. Let's just say I'm a geek from Brooklyn who probably loves .NET and databases, hopefully as much as everyone else on the call. And I hope I hope you'll appreciate the presentation that I have for you tonight. Now that I've introduced myself, I would like to cut the video and request all others to do the same, because that will really make a difference in bandwidth for making sure that the screen comes through and the audio comes through, and I shall do the same. I'll also throw out a tip. If you hit the 3 ellipses, you can view my desktop full screen, which can be helpful if you want to do that as well. Okay.
All right, Nathan, do we have to switch it over to him for that? Nope. Good.
No, he's got it. Yep.
So welcome again, and my name is Lenny LaBelle, and I'm here to talk about building event-driven microservices with the Azure Cosmos DB change feed. That's a mouthful. We'll break that down. Let me move that guy out of the way there, and let's just jump right in. So again, my name is Lenny LaBelle. I am a Microsoft MVP data platform. It's almost 10 years now, and I run my own company back in New York. I'm here in New York. Sleek Technologies, and I'm also a principal consultant with Talon. Lots of training and speaking and writing, and I've been doing this for a long time, since '79. There's my contact info. The books on the right are kind of old, but nowadays I'm doing a lot of Pluralsight courses. So there's actually newer SQL Server content, as well as a lot of Cosmos DB content that I've got out on Pluralsight as well. There's my contact info and more than enough about me. So here is a link that is actually active. It's a bit.ly link, and it's TVUG 2020_Cosmos_CF for change feed. This is primarily a discussion about the change feed and using the change feed to build microservices. And if you go to this link, you'll hit my OneDrive, and then you can download a zip file, inside of which you'll find this deck and all the code, which is a lot more than we'll be focusing on tonight, of course. So with that out of the way, let's just talk about this evening's objectives. Of course, we're going to have to lay some groundwork with Cosmos DB. I don't want to assume any prior knowledge. Obviously, it's great if you do have some, but if you don't, we will definitely lay the groundwork first by reviewing the core, the most important concepts in Cosmos DB, which is namely partitioning. So we're going to review that and then talk about the change feed and learn about what it is and what it can do for you, and how you can build microservices on top of it. And by consuming the change feed, you wind up basically building event-driven microservices. And again, if that's we'll demystify that if you're not sure what that means. So what is the change feed? In Cosmos DB, you store data in a container, and data is in the form of a JSON document. The JSON document goes in, but every time a JSON document goes in, the change feed emits that change. The thing is, it also persists it, so you can always rewind the change feed and replay the events of that container. Okay, and that enables many scenarios. Okay, for instance, replication. There might be cases where you need to replicate a container in its entirety, and we'll talk about why you might want to do that. Like, why have 2 containers with exactly the same data? Well, because you need to pick only one partition key for a container, and if you need to pick 2 partition keys, it could make sense to have duplicate copies of your data, each partitioned differently, and so you might want to consume the change feed to replicate one container to another. Denormalization is another very common use for consuming the change feed. A lot of folks mistakenly think that Cosmos DB is not suited for relational workloads, since it is a non-relational database, and there's no joins, for example, and many of the things you expect, and so they think it's not suitable. But in fact, it is, if you just think about things differently, and one of those ways is denormalization, where you strategically duplicate pieces of data so that you can cut down the number of queries instead of making multiple requests, for example, just making a single request. You're going to see examples of all of this. Certainly, you can listen on that change feed and watch the documents go by and observe for anything of interest that you might want to send a notification for. So that's clearly a use case for this. Materialized views is a very important concept, and we're going to see what that is and what that means exactly and why it's so important in Cosmos DB. But again, you can consume the change feed from one container and materialize a view by watching the events as they occur and materializing a view that is then easily consumed by a large number of consumers. Finally, there might be any number of downstream processes or downstream systems that you might want to feed data to as it enters your container in Cosmos DB. An example might be a legacy application that doesn't have access to your Cosmos DB account and doesn't know anything about Cosmos DB and is just using your relational database like Azure SQL database. You could watch the container and keep a relational table in sync with the changes in the container so that that application can then consume that data, and it's in near real time that it will be updated. So you can you can think of each one of these things as an individual microservice. And if you're not sure what a microservice is, it's just kind of a way of breaking your application down into individual, single responsibility pattern, basically. So you have a microservice is responsible for one thing and only one thing. And what's really nice about using the change feed on a container for microservices is that it serves as a single bus, if you will. It's a single event hub. And maybe that's not a good term because there's also, the Azure Event Hub, but that's not a database, right? That's just for eventing. Cosmos DB is a full-fledged database. And so it serves as a single source for any number of microservices, and there would be many microservices running independently of one another, all consuming the same change feed. And that's a much simpler architecture overall than when you have microservices communicating with one another and having dependencies on one another. And we're going to see how we can create independent microservices that consume the same change feed and yet are still entirely independent. So let's jump into, as I said, reviewing the basics, because if you don't understand partitioning, it's going to kind of be hard to follow along with any discussion around Cosmos DB. So we talked about the concept of a container, and that's a logical resource. We store data inside a container, and that's our perspective. But behind, we just have one container that we interact with, but behind that container, there sits a cluster of servers that is managed by Cosmos DB, and that we generally don't concern ourselves with. We only concern ourselves generally with the container. But as we flood our container with data, if it's going to be a large amount of data, like big data, terabytes, petabytes, Cosmos DB, and not just storage, but also throughput. Cosmos DB will just add more servers and more servers and more and more. This is the essence of horizontal scale, because each of these is, each of these servers, if you will, is essentially, a box, each with its own CPU and disk storage. So, you can really get unlimited storage and unlimited throughput by just, simply scaling out. So, each one of these black boxes here is really just like a machine, like any other machine. But we can also call them physical partitions, and that's what we call them in Cosmos DB. They don't mean exactly the same thing, because a physical partition is also a unit of replication. And by that, I mean the internal replication that Cosmos DB provides on the back end to ensure the availability of your data. It actually, replicates each one of these physical partitions. But for all intents and purposes, let's just say a physical partition is a computer that has a CPU and disk storage. A limited amount of disk storage, but there's an unlimited number of servers in the cluster. So, like I said, there's this bank of servers sitting behind a container. And if we zoom in a bit and we start storing documents in our container, they're going to land on any one of these partitions. And is it arbitrary? No, it's not. Like, how does Cosmos DB know like which physical partition to store which particular document? It's not arbitrary. So that's up to us, the human, if you will. So Cosmos DB manages the physical partitions, but we're in control of what I would call the logical partitions. We define a property in our data, and every document is going to have. Now, if you're not familiar with NoSQL, you should know that all of these documents can be of different types. There's no enforced schema of what properties and the shape of the JSON in any one of these documents, but they're all going to have a common property that the value in that property is going to define what logical partition that document lives in. And so when you create a new container, you're going to be asked for that partition key. And I'm just going to go with an example now of a social network, where if I use the username property as the partition key, that would mean, and let's just forget again about the physical partitions, because it's usually helpful to forget about the physical partitions and think just in terms of logical partitions. It would mean that all of the documents belonging to a given user would be contained inside the same logical partition. All of Tim's documents in one, and all of Andrew's in another, and so on. And again, in the social network scenario, these documents could be all different types. So in each logical partition, you could have one and only one document that would be the user document, and then a set of documents that could be the posts belonging to that user, and then a set of other documents of different types, like the comments and the likes, all of which share the same username property and therefore live in the same logical partition. Now, a logical partition will never span physical partitions, and you're never going to want to, certainly bloat one physical partition, and you don't want to pick a partition key that gives you nice uniformity, and we'll be talking a little bit more about that. But Cosmos DB will, like I said, as the database grows, it will add more physical partitions, and the way that it does that is by doing a split. In the relational database world, that sounds bad because a table split is a bad thing if it happens too often. But here, a partition split is a good thing. Cosmos DB will, in real time, take any partition and literally split it. It'll add a new partition, and it'll take half, roughly, of the logical partitions and move them over. Okay. So we'll shuffle these logical partitions around, and we don't care about the mapping, and it's of no concern to us. But it'll never span physical partitions. So let's look at some common partitioning patterns. For a write-heavy scenario, like we're going to be looking at, it's very common to use the ID property itself as the partition key. And that's a very odd pattern to many people when they hear it the first time, because it really means that you get one and only one document inside each logical partition. And the reason for that is because in Cosmos DB, every document is unique in a container based on a combination of, a composite of this ID property here and whatever other property you choose for the partition key, like the username, for example. But if you go ahead and choose the ID property itself as the partition key, it's basically unique just by the ID, right? And you only get one document in each logical partition. And it doesn't seem like a good pattern at first because, well, from a querying perspective, any query where you need more than one document is definitely going to span logical partitions, and you always want to avoid those. But for a write-heavy scenario where you're consuming, let's say, IoT telemetry, let's say like from airplanes, like we're going to see later, or it could be elevators, or it could be, automobiles or delivery trucks, anything like that, that's constantly emitting this telemetry at a very rapid rate, ID is going to be a very good partition key. Maybe not so much for querying, but for ingestion of a massive amount of data. It's not always a massive amount of data, though sometimes you just have these small lookup lists. I mean, if I'm running an airport, the telemetry for all the flights that are in the air is a massive amount of data that won't fit in the logical partition, which, by the way, is limited to 20 gigabytes. So, every time you see one of these blue dotted rectangles, the maximum capacity is 20 gigabytes. But just my list of flights, I mean, if I have 10 flights, 20 flights, 100 flights that I run, I mean, I'm not, these are small JSON documents. I could store all of them in a logical partition, like all the airports that I service. Again, lookup lists. If I'm running a web store, I might have product categories, right? A whole list of product categories, but they'll easily fit in one logical partition. And tell me what application doesn't have a list of states and provinces, that sort of thing. So those could also go themselves into their own logical partition, and you could just have a type property on all of these documents, and every flight document has the value flight, and every airport document has the value airport, right? You put the name of the lookup list in that type property and thereby group. And therefore, it makes it possible to, let's say, consume the entire lookup list if you want in a very efficient query. Because if you know the logical, if you know the partition key is always going to be, then always, if you know the partition key, then Cosmos DB is always going to know which physical partition it is, right? And then it's always going to know where it can find all the results. In all other cases, you really need to know what your patterns are. I'm not going to go through all of them. I'm just going to give you one example where the customer ID might be a good idea to use, where again you'll store multiple documents in a single logical partition, but all those documents belong to the same customer. A single document for the customer and all that customer's orders. So all of a sudden, the whole concept of the fact that you don't have joins. Well, if I need a customer to know the orders and they live in the same logical partition, then I can retrieve them efficiently in a query that is roughly equivalent to the efficiency that you get in a relational database simply by saying join and getting them in a single query instead of having to query separately for customers and orders. Of course, once you need to span multiple customers, that's no longer the case. This is another really critically important concept that I'm going to hopefully make it clear by the animation that I put together for this. So there's multiple physical partitions, right? But I also said that there's a single change feed. So there isn't a single change feed. Just logically, there's a single change feed. Just like logically, there's a single container. But there are multiple physical partitions behind the scenes, and there are therefore indeed multiple change feeds behind the scenes. So here's the scenario. And with Cosmos DB, you are free to model your data any way you need or wish. You can be very creative. I'm going to model a shopping cart here, but not in a stateful way. I'm not going to have like a shopping cart document that has all of the items in it that I'm going to insert the first time and then update as the user shops. But rather, I'm going to model an event-based database. So anytime a user does something with their cart, when they add an item to their cart, I will write to the container. If they remove an item from the cart, I'm not going to delete that first item. I'm just going to add another document that describes the deletion of the previous document and so on. If the user changes the quantity of a previous cart item, that's another insert. So no updates, no deletes. When the user finally checks out the carts or checks out their cart or throws away their cart, then that's another insert, it's another event. So if customer A comes along and adds their first item to the cart, it's going to be a document representing that event, and if it's the first document for that customer, it will also create a new logical partition. And then another customer comes along, and Cosmos DB will put it on a different physical partition, but we don't care. But you see that when it does write these documents, it also writes to the change feed in the order that these changes occur. So now if the second customer adds another event, it gets written to that change feed for that physical partition, and the third customer comes along. You see how this is progressing, right? A fourth customer has come along, and now the events are coming in overlapping one another, but they're being recorded in the order of the logical partition, which is the cart ID, right? If you will, each cart is associated with the customer, but each logical partition is a cart. And we're partitioning on the cart ID, and we're recording every event. Now, at this point, if a fifth customer came along, Cosmos DB might want to do a partition split. So it might, we now need shopping cart E, and Cosmos DB will split that second physical partition and move, and remember, right, each physical partition gets its own change feed. So it'll move roughly half. I only have room on the slide for one logical partition, but it'll be roughly half of the logical partitions. But that's why you want good granularity. You don't want some logical partitions that are huge and some that are tiny. That's not going to be a good pattern. You want you want to pick logical partitions where it's easy to shuffle them around and you get good uniformity. So roughly half would move over, but then of course the change feed events must move over as well, and they do. They migrate over at the same time, transparently. preserving their order. And so now we get a new logical partition on physical partition 2 for customer E, I should say cart E, and its first event. And this proceeds to go on. And more partition splits can occur and will occur even as users are shopping. Even as customers are shopping your e-commerce website, physical partition splits are happening the way we just saw. But what you can see is that in spite of that, you're always going to be able to consume those events in order. You're always going to be guaranteed that they're in order within a cart, right? Within a cart, the events are always going to be consumed in order, and that's what matters, right? The order of the carts themselves doesn't matter, but the order of the events within a cart is what matters. So you can see that no matter how this thing scales out, and because the change feed is persistent, you generally try to keep pace with the changes as they occur in real time. But if for some reason you want to rewind the change feed or go back in time or reprocess events, you can always go back in time. And if you do that, no matter how much time has elapsed, no matter how many splits have occurred, you're guaranteed to process those events in the proper order. But again, you're not going to be processing 3 change feeds. It's just one logical change feed that you're going to get. So if you interleave the events of these 3 physical partitions, you're going to get the logical change feed on the right. But still, if you just look at each cart ID, the events are in order. And that's obviously very critical. Because again, remember, if the third event represents the modifying of the quantity of the item that was added by the second event, clearly the event needs to be processed in order. And your microservices are doing things for an order. This is an order processing pipeline example, where your microservices, one's calculating sales tax, one's handling the shipping, one's handling the stock checks, all these individual microservices are consuming the change feed to handle the real-time shopping cart experience. So I'm doing a quick time check, and I see that I am pretty much on time. I want to make sure that I'm still live. I haven't lost everybody.
Yeah, you're good.
Oh, okay, great. So hopefully everything's clear. I think we're going at a good pace. Will be good time for Q&A at the end, hopefully. So let's just move ahead and see how are the different ways that we can consume the change feed. There's 3 ways. You can do it directly. And I mention this only because it is technically an option, but you really do not want to do this unless pain is something you enjoy. It's possible. I have an old blog post that shows you how to do it, but then you're dealing with page splits. You basically are consuming each change feed from each physical partition yourself. You're keeping track of physical partitions. You're getting your hands dirty with physical partitions and partition splits, and you're going to have to somehow persist your own state if you want to be able to keep track of the last time you checked for changes on any given physical partition. You're going to have to store that somewhere. You're going to have to do a lot of work to scale out and parallelize the workload as once events start coming in fast and furious from IoT telemetry, for example. You're going to have to do all that work yourself. It's a lot of work. So to avoid all of that housekeeping, our good friends on the Cosmos DB team gave us the change feed processor library, which I'll often just call the CFP library. And this gives you, this answers all of those problems that I just, all of those pain points that I just enumerated. So it handles the state. You'll see that there's a container that it calls the lease container, where a lease is nothing more than just a document that keeps track of, when each physical partition was last checked for changes, the work that you would have to do yourself. It handles that state, and it scales automatically. That's the beautiful part. You just have to, you're only concerned with one thing, right? Your business logic. What is it that I need to do on each event? And you don't want to have to start writing threading code and auto scale out code. You want scale on demand, and that's what you get with the CFP library. It will scale your change feed processing as Cosmos DB scales your container. And then there's the Azure Functions option, which, to be clear, is not really a different option. It's just a wrapper around the CFP library. So all of the aforementioned benefits of the CFP library, you're still going to get those when you go with Azure Functions, plus let's say benefits or the ease and simplicity of serverless deployment. It is the simplest and easiest way to deploy your microservice. You know, you can go with the change feed processor library, but then you have to host it yourself. But if you go with Azure Functions, it's really, really simple. We'll see how that works as we move forward. So we're going to jump in and look at our first microservice. And that is going to help us cure the analysis paralysis problem, which is to say that when you create a container, you have to choose a partition key. And like we said, you have to, you know, examine your most common querying patterns, and then based on that, like the customer ID example, if you're frequently querying for a customer and their orders, well, then the customer ID is a good partition key, right? So you would choose that. But here's the thing, you know, you can only choose one. And what if after all the analysis you just can't settle on one, because it turns out that, you know, half the time you're running these types of queries where you would benefit from choosing one property as the partition key, and roughly the other half of the time you're running a different category of queries where having chosen a different property as the partition key would benefit you. So you're like stuck a bit. Now, I want to be clear, these cross-partition queries are not evil in and of themselves. The occasional cross-partition query, when it happens here and there, not only is there nothing wrong with it, I mean, you're never really going to be able to completely avoid it, and that's fine. It's just those very common queries, especially the ones that are constantly hammering away at your container. If you're constantly hammering away at your container with two different types of queries, you have a quandary. And the way that we solve this is through replication. We will just synchronize two containers with the same data, partition differently. Kind of was explaining that earlier, but now you're going to see an example of it here. So I've got a cart, and now I'm storing, let's say, stateful cart data in there. So every document has the ID of the cart. That could be some parent cart document, maybe, and the item and the quantity, right, for that cart, ABC. And I'm partitioning this cart on cart ID. That means I can definitely query for all the items in a cart by cart ID, and that'll definitely be a single partition query, and that's great. So, for instance, a query like so: give me all the items in cart ABC. Definitely no problem, because the partition key is known. Cosmos DB knows which logical partition and therefore which physical partition to route the query to, and it doesn't have to visit all the partitions and fan the query out and aggregate the results, which, you know, is more expensive. That's what's called a cross-partition query. And I can also further filter within a cart, like, you know, within a cart, I need all the, you know, run a query that within this cart gives you all items with a quantity greater than 5. Right? That would also be a single partition query if you filter within the cart. But what about a query like so? I want all the items in this cart container for Surface Pros, right? And that's going to be across many different cards, A, B, C, D, E, F, and so on. So that's going to be very expensive. And again, here and there, it's going to be fine. But if you're hammering away with these queries, you are going to benefit by replication. There's definitely a cost to this replication, and that's why I'm emphasizing that you only want to do this when it's a very read-heavy scenario. But when it's worth incurring the cost of the one write that you do when there's a change against the, you know, the savings that you're now going to get by being able to run that second query against the second container instead of the first, and it being much more, you know, much cheaper, you know, that's when you go with replication. So it's important to understand how how updates and deletes work. Actually, guys, let me just pause for 1 second. I just want to check something real quick on my solution here. Yeah. Okay. Sorry. So it's important to understand how updates and deletes work. For updates today, interim updates are actually not retained. So if you think about the eventing model, where every document that you write represents an event, then that's not an issue. There are no updates. There are no deletes. If somebody wants to delete something, then it's an insert that represents the delete, right? So, and for, let's say, any kind of IoT telemetry, it's always inserts. You're just constantly ingesting. You're just constantly inserting all of the device telemetry as you're receiving it. So then it's all fine. But if it's a stateful scenario, you need to be aware that if you update a document, that you lose the previous update, and that's today. And again, for our replication scenario, it's not going to matter, because if we only need the latest version of a document, and even if we lose the replica container and we have to rebuild it from scratch by rewinding the change feed, we still only need the latest version, so that's fine. Deletes, on the other hand, are a problem somewhat, because they are today, again, not into the change feed. I keep stressing today because the team is working on changing this behavior, but right now deletes aren't written. So what we're gonna do in order to process deletes is we're going to rely on a feature called time to live, TTL. So I've worked hard to put together some of these slides so that we can skip some of the demos, that it's visually conveys the point well enough. I want to save the demos for the for the heavier content that's coming up. So I'm going to skip the replication and denormalization demos and just rely on the slides to make the point. So obviously the cart by item container is partitioned on the item property, and if the quantity in the cart container gets changed from 2 to 3, like you can see in green on the left there, clearly we need to pick that change up. And we just have a microservice that does it. I'll show you the code without running it, actually, right? And if the quantity changes from 3 to 4, then obviously we'll pick that change up as well, and then we'll be able to update that document in the replica container. But the cart container's change feed no longer has the version of the document with the quantity of 2 and 3 in it any longer. But that's, again, fine for us. Now we want to delete this document, let's say, and we can't, as I said, just go ahead and delete it from the cart container because it won't get picked up by the change feed. So the solution is to use this TTL, time to live. It's a capability where it auto expires the document in Cosmos DB if you enable it on the container. This is saying delete within 60 seconds. Now 60 seconds is way more than generous. You only really need 5 seconds at most in many cases. But that's if your service is microservice is constantly running. If you want to allow leeway, if you want to allow for possible downtime, you want to play it safe, even 60 seconds is too short, one might say, in that event, because you don't want to miss this update. Because what's going to happen is you're going to pick up this change almost immediately, and your microservice will just go ahead and delete that container on the right. Delete the document from that container on the right. But Cosmos DB will then automatically go ahead and delete the document from the container on the left 60 seconds later. And if for some reason the microservice wasn't running during those 60 seconds, Cosmos DB will still delete that document. And then even if your microservice comes back up, you will have lost your opportunity. You lost your chance to delete that document, and you'll wind up with essentially orphaned deletes in the cart by item container, which you don't want. So just make the TTL long enough to allow for reasonable potential downtime. But in worst case scenario, you can just throw away the replica container and rebuild it from scratch by rewinding the change feed on the left. So using Azure Functions, I'm going to show you this microservice. I'm just going to show you the code for this microservice now without running it as an Azure function, because we talked about the CFP library and all the benefits that it provides, but you still need to host it yourself. Like in the traditional sense, it's not a lot of work to get it done, but you still need to do it. It's either going to be a web job or an app service or a cloud service worker role, and you're going to get the dedicated capacity that you purchase, if you will, with the plan for that resource on Azure, and you can just host your CFP library there. It's not a lot of work, and it's very run of the mill. But the, can I say, sexiest way nowadays of doing this is with an Azure function. And these are essentially serverless, meaning you just deploy the function, right? You write these individual functions in C#, as you'll see in a moment. You just deploy the function. Perhaps you're familiar with them because there is quite a number of triggers available to run an Azure function. Of course, the one we're interested in is called the Cosmos DB trigger. That's the one we're interested in. And with Azure Functions, you do get shared capacity. You need to bear that in mind. If you ever worked with Azure Functions, they're prone to cold restarts if they sit idle for too long. and all of the other unpredictability that comes with shared capacity and a consumption-based model. So if you need that, those guarantees, you can either, again, go with the CFP library and not use an Azure function, or you can actually pay for Azure Functions Premium, which gives you a lot the same dedicated capacity and therefore the same benefits. So knowing that the Azure Functions Premium option is there if and when you need it is just another great reason to go with Azure Functions. So let me show you the code for this replication microservice. Without actually running it, I'm just going to show you what the code looks like. We're going to run. Let me just show you the sample code that I have for this session. This is these two change feed functions. We have two microservices in them that I'm going to show you now. And then we have these Contoso airlines that we're actually going to run those. But if you look here, I've got one project with two functions in it. We're going to first look at replicate card function. And let me make it nice and big for you. You can see that it's ordinary C#, okay? And I've got a Cosmos client here that I'm going to need in order to be able to write to my replica container, which I'm going to initialize here in the static constructor, where with an Azure function, the get environment variable, think of that very much like web config or app settings JSON in a traditional .NET app, but in the case of Azure Functions, it's local settings JSON. And like the name says, it only applies when you're running locally. So any configuration that you plug in here will have to also be plugged into Azure when you deploy this microservice to the cloud, because this is only for local. But there's my account endpoint. It basically points to my Cosmos DB account that has a master key in there that is, you don't generally want to share, of course. And it gets that, and now I've got a client that I can use. Now, the function itself, this looks big here, but it's a very kind of a little bit of a strange syntax where the Cosmos DB trigger attribute is inside the signature of the method body. Okay? So we're accustomed to seeing our methods being decorated with attributes. So if you take any method and decorate it with a function name attribute, it becomes an Azure function. That's just automatic. And then depending on which type of Azure function trigger you go with, you're going to plug in one of these attributes here. You're actually really only being handed these two parameters, which are all you need. A read-only list of the documents that have changed. It could be one if things are happening sporadically. It could be a bunch if there was just a bunch, a spike, or it could be a bunch that have been split up for you automatically on multiple threads by the CFP library, where you don't have to do any of that work. You have a list of changes. It could be one, it could be many. It doesn't matter. You want to process each one, and a logger for you to log events. And inside, it's very simple logic. We are looping through. We're getting a reference to our target container. So the container that we're looking for changes on is called cart. The container that we want to update is called cart by item. And collection here is just the old name for container. Can you hold on for a second, guys? All right, sorry about that. This is the name of the leased container, and we're going to have a look at that as well. Again, that is for the CFP library to manage state so that you don't have to. You don't really need to do anything other than just have a container and give it a name, and it's very common to just name it lease. This is very important. You're going to see that each of our microservices is going to have a unique lease collection prefix. You're going to see that is going to allow us to share the same lease container. We can have many microservices consuming the change feed at their own individual pace, or each at different points perhaps some stopping and then starting and therefore needing to catch up. But each one can share the same lease container. You'll see for all our microservices, we're going to have the same lease container. We're just going to have a different prefix, which I just like to name after the function, just for sanity's sake. But the point is that it allows you to uniquely isolate the bookmarks that are stored in the lease container for each of the microservices. Now this start from beginning equal true. Once you have a state in the lease container, it's going to be ignored. But if you don't have state in the lease container, then when you run this for the first time, this is going to actually rewind from the beginning of time. This is only for demos. In the real world, you'll never have this. It's just for demos. You will normally want to explicitly create the lease container yourself. So what am I doing? This is, look at all, the code itself. This is all of it. It's a simple for each, where I'm checking the time to live property. I'm getting all the documents that change. Time to live, if I peek at the definition, you can see it's mapped to that TTL property I was telling you about. Just the .NET gives it a friendlier name, but it is that TTL property, that magic TTL property. If it's null, then it really is an update or an insert. But fortunately, there's a convenient upsert item method, and everything's asynchronous. So it's a TPL everywhere, async and await everywhere, and that's it, But of course, if there is a TTL, that means the document is about to expire from the card container. We need to delete it. How do you delete it? Well, to delete any document, you need two things: its ID and its partition key. And we know that this container that we want to delete the item from is partitioned on the item property. So we get that string property value from the document, and that's our partition key. And the ID is the ID, and then we just delete it. And that's it. That is the microservice. So let me just do a quick time check. Okay, we're doing good. We're going to move on to denormalization. Handling relational workloads, we talked about some of the challenges. So there are no joins. Well, we saw how we could solve some of those problems by partitioning in a way where most of our common queries, we can get documents of different types kind of joined, not really joined together, but at least efficiently retrieved in a single query, in a single request, similar to the way you get a join in the relational world. There's also no relational constraints. I mean, think about documents spread across different physical partitions and the overhead for having to establish, constraints on those. So, you don't have any of that. So you just have to think about things differently, and denormalization is one way. You can also embed JSON arrays for one-to-few relationships versus one-to-many relationships. And if you'll pardon the plug, you can learn more about it in this Pluralsight course that I have that really walks you through the process of refactoring like AdventureWorks for SQL Server to a non-relational data model in Cosmos DB, including a discussion about denormalization with the change feed, which is what I'm talking about now. But if you're interested, you can check out that course. And I also have my overall learning Cosmos DB course if you just want to, in general, learn all about global distribution and all of the other good stuff at an introductory level. So putting that aside, we want to denormalize. What that really means is strategically duplicating certain properties so that queries that would normally require multiple requests can now be satisfied with a single request. Here's an example. I've got a product container. It has products that look like this. There's a bunch of IDs in there. Of course, there's the ID itself, which is the product ID. But there's also the category ID. And then there's an array of tag IDs, right? String array down there of tag IDs. So if I have one of these documents in hand, I really don't have everything I need, do I, to display the product on a web page, including the name of the category and the names associated with those tag IDs, because that information is stored in a separate container, let's say the product meta container, partitioned on type, where I've got category documents, like a lookup list, and tag documents, like another lookup list. And if I want to get the names of those tags or the category name, I need to retrieve those documents as well. In the relational world, we would just think of the category ID and the tag IDs in this document simply as foreign keys that we can join on to get that extra information, but that is not the case, of course, again here. So if I wanted to get all of the products in a particular category, I could run this query on the product container, and if I partition on the category ID, this would actually be a very efficient query. I would get all of the products in a single category in a single partition query that would be efficient, but then I would need to run this other query just to get the category name from the ID. And then for each tag ID, I'm sorry, for each document, I should say, for each document returned by the first query, I would need to run the third query, where the in clause in this query lists out all of the tag IDs in the array in order to get the tag names. And that obviously sounds very painful. And with the lack of joins, you know, isn't there a better way? There has to be a better way. And that is, again, through denormalization. Thinking very differently than the way you do in the relational world, where you would never duplicate data. Here, we're going to duplicate data. We're going to do exactly that. So every time we create a product, in addition to the category ID, we're going to store a copy of that category name. A copy of it. It's a duplicate. The master category name is in the meta container still. And instead of just having a string array of tag IDs, it will now be an object array, because each tag is going to carry not just the ID, but also a copy of the name. Again, duplicating the name from the master tag document in the meta container. And that means that if I have a product document, I have everything I need to display, but it also means we need a way to cascade updates if a product name changes or if a tag name changes. So for example, if I have a product container with all of these products in it, you can see the category name shorts after the category ID. And you can see the tag IDs also carry the tag names. Those are copies. Then the product meta container has the master documents. So, I mean, each category could actually have much more information than just the category name translated from the ID. It could have a parent ID if you were doing this in a hierarchical way. It could have other information about the category. But it's really just the name that we need duplicated. Same thing with tags, right? So what we want to do is we want to listen to the change feed on the product meta container, so that if any change that occurs to a master document gets propagated or cascades, if you will. So if shorts, let's say, gets changed to fun shorts in this one document, we want to update all of the documents on the right. I'm only showing the, yep, I'm sorry, actually, I went ahead of myself with the PowerPoint animation there. So if shorts is changed to fun shorts, and this tag outdoor gets changed to outdoors, we would need to propagate that to all of the documents here. I'm only showing this one on the top, but there could be many other documents responding to one change on the left. In the case of the category change, we want to change the category name. In the case of a tag, we want to find the element in the array that matches on the ID and change its name without disturbing the rest of the array. So let's look at the code for that. And what you're going to see is something very similar, denormalized product function, very similar to what you saw. Well, actually, if you look, if you go back to like this diagram, it's similar to replication, but very different. We're not duplicating one container to another. We're picking specific properties. And it's not a one-to-one change like the replication. With replication, every one event was one change, either an upsert or a delete. Here, one event could be multiple changes, right? So it's similar to replication, but again, using the change feed. And this is an individual microservice that runs independently of the replication microservice called the denormalized product function, the denormalized product microservice, if you will, which also needs a Cosmos client in order to be able to write to the target container. But we are watching the product meta container, right? We're watching for changes to products, to categories and tags. There's the same connection string as before. It's the same database. Everything's in the same database. Same lease container, but with a different prefix so that the denormalized product microservice and the replicate cart microservice can independently maintain state in the same lease container that they're sharing. And right, even though one of them is watching, this one's watching the product meta container, and the other one's watching the cart container, that also doesn't matter. So again, it's the same thing. We're being handed a list of documents. Now let me talk about the try catch here. This is really important. Obviously, it's just a demo, so I'm doing a log error. But in fact, you need to you need to do things that you need to handle exceptions. If you don't have a try catch, what's going to happen is if you're using the CFP library, it will simply retry. That could be nice if it's a transient error, but more often than not, there's something wrong with that piece of data, and it will retry infinitely. That's not good. And in the case of Azure Functions, because Azure Function just cares about running constantly, it'll just swallow the exception. That's also not good. Neither case is good. So the recommended practice is to first of all, you want to keep your microservices as light as possible and have them do as little work as possible to minimize the risk of exception. But you want an exception handler around each individual change. So I always have this top level method, calls the work that could potentially throw an exception. And here you should really just tuck away the fail document, some queue somewhere, or maybe an error container. Just don't try to reprocess unless you think you can. And because events could be flooding in, and you can just deal with it later. So we're going to process the change on each one, and we're going to get the document, and we're going to deserialize that to a dynamic. I know you all know what that means because this is a dynamic user group, but this could also be a POCO. But it really couldn't, right? Because this is NoSQL, and we, one document, could be a category document, another one could be a tag document. So having a strongly typed class here isn't going to work very well, is it? So we're going to deserialize that into a dynamic type, and pardon the pun, examine the type property, which will have the word category or tag in it. And then I'll know whether I need to update product category names or product tag names. So let's look at updating product category names. For one change in this category ID to this new name, I need to update all of the documents in the product container. Now, these are all going to be all the products in that category, right? So this is going to be a very efficient single partition query, right? And I'm going to run it against the product container. Because this is a single partition query, I'm going to supply the partition key. And that's going to make it very efficient. It's going to get all the products in that one category, all of the documents that need to be updated. And the pattern is that you get an iterator that, if you check has more results, you keep iterating while there are more results. Each iterator gives you a page that you read from. This is actually doing the I/O. And then you for each through each one. And what am I doing for each one? This is in memory. Oh, by the way, this is a hack on my part. These aren't warnings. In production, you would never do that, I hope. Only log a warning if it's really a warning. But actually, it paints it yellow, and it makes it much easier to see fly by. So in demo land, it's great, but in the real world, it wouldn't be a warning. It just makes it easier for us to see the output. So this updates the category name in memory, and this replaces it in the container, and that's it. The product tag name is similar, but a little more, savvy. Well, first of all, it's not as efficient a query. We need to find all of the documents. Remember, we have a tags array. And we need to find any document where in that tags array it contains an object where the ID matches the tag ID that changed. And that is going to span multiple logical partitions. That is a cross-partition query. So the options this time don't specify my partition key, because I don't know the partition key. Instead, I set max concurrency to -1, and that tells the .NET SDK to parallelize the cross-partition query in order to help speed it up. So again, is it evil? Well, how often are tag names changing? Here and there? No problem. On a constant basis? Well, you need to rethink things. So I'm just showing you here a cross-partition query. But otherwise, the pattern is the same. You get an iterator. Each iterator gives you a page. In this case, this one line of code here is finding the tag object inside the tags array, matching on that ID, just finding that one, because I know that the tags array is an enumerable of dynamics. And then I'm changing the name of that one tag and replacing it in the container. And that is your denormalization microservice. Now it's going to get a lot more fun, because we're going to move into a very heavy IoT scenario. We're going to be looking at a lot of data coming in fast and furious, and we're going to also be running the demos, not just looking at the code. So we're a small airline today. We hope to grow, but right now we just have 12 flights and 6 airports within the US. But even with those few flights, that's a lot of IoT telemetry. If those planes are all flying in the air at the same time, and each one is broadcasting every 10 milliseconds, its speed, altitude, and longitude, and latitude, well, yeah, that's a lot of data to ingest. So let's look at our requirements. Well, obviously, I think anyone can figure out we need real-time flight info. I need to know for any flight where it is, how fast it's moving, what its altitude is, and its latitude and longitude. I want to be able to maybe have a nice map where I can show that on a map, whatever. I need that real-time flight info, obviously. We have some designated no-fly zone alerts. You're not supposed to fly in certain areas, so we want to get notified anytime a plane enters a no-fly zone. We need up-to-date arrivals information. We need to display arrival boards at all the airports. There could be other consumers that are constantly interested in up-to-date arrival information. And let's say we have this requirement of permanent archival, like permanent, like it's mandated by the government that, you know, long after a flight has landed, years and years later, we need to be able to look back and say that at a given point in time, a flight, the statistics for that flight or the telemetry for that flight. Well, we don't want to keep it in Cosmos DB forever. It's just not necessary. After a month, let's say, is enough in terms of running queries on flights of the last 30 days. But beyond that, you know, we need a better way to archive it. Our solution is to well, first of all, we're going to ingest all that flight telemetry, and then, of course, we're going to implement microservices. And we are going to watch that change feed and email alerts if a plane enters into a fly zone. We're going to create materialized views, and you can see what that is. And that's going to allow us to get very efficient real-time flight information and up-to-date arrival information. And we're going to have another microservice that will archive to blob storage so that we can leverage that TTL feature that I was talking about and keep each document around for 30 days in Cosmos DB, but meanwhile permanently stored in a much cheaper cold storage. And it could be anywhere, and I've just chosen Azure Blob Storage. So how are we going to do this? We're going to have a location container. And it's going to receive all the flight telemetry, fast and furious, all of those statistics, right? Every 10 milliseconds per flight. Now, we are going to partition this container on the ID property, and we're going to be using a GUID for the ID. Remember, that's going to give us exactly one document per logical partition, and this container is going to fill very, very fast. And yes, it may not be optimized for queries. You're only going to have a single document in every logical partition, but it is going to give you the largest possible spectrum of values for a partition key by virtue of absolute uniqueness of a GUID. And that is the best way that you can ingest data at high speed, at high velocity, and high throughput. So let's have a demo. Let's have a live demo. Now, I will confess I don't actually have a fleet of planes, but I do have this cool simulator that I wrote. For Contoso Airlines. I'm going to run it. And I'm also going to flip on over to the portal, which looks like I hadn't opened up the portal. I'll have to go there. Okay. There we go. And let me show you a few things here. Let me go into the Data Explorer. And you can see I've got two databases here. The Acme Web Store database has containers that show all of the examples that I didn't run. I just showed you the code for. But let's have a look inside the lease container. And let's look at the items in there. So you can see that there's very few documents in there. And it's really going to be one document per microservice plus one document per microservice per physical partition. This is a small container. There's only one physical partition. But every document is prefixed. The ID of each document is prefixed with the prefix I gave it. So I have a CFP library demo that shows how to use the CFP library. I didn't show you that, but I did show you the replicate cart. I showed you the replicate cart microservice. Remember that lease collection prefix, that lease container prefix? There it is. So that's uniquely scoping, and this is a timestamp for when this particular partition was last checked for changes. Again, you don't need to understand the content here. What I'm showing you is the isolation of the different microservices. This is a different microservice that has checked that partition for changes, perhaps at a different point in time. And they're all sharing the same lease container. So that's the first thing to show you. That's in the Acme Web Store database. In the Contoso Airlines database, we're now only looking at we have the same lease container that is going to be shared by all the microservices. We're doing the first one now. Well, we're not doing any. We haven't done any yet. No microservices yet for Contoso. We just have this location container that you can see has got tons of documents in it because it's got 20 million documents in it already. I'm just going to keep adding more. I'm going to hit generate continuous, and you can see what's happening here. Actually, am I running it with the debugger? This is running way too slow. Huh. Maybe it's because of the Teams meeting and the screen capture, but I'm usually up at 160 per second here. And basically, this actually usually runs much quicker, but it's just pumping in telemetry. I'm not really going to go into the code of the generator. It's not really relevant. It's just I've put some nice things in there to help it simulate the real world. And if you go flip on over to the container, these are the types of documents that are being flooded into this container. You see each ID is a GUID. Each one of these is living in its own logical partition, but they are telling you at this point in time. So down here, these are not our properties. The ones beginning with an underscore, these are Cosmos DB system properties that we normally don't need to worry about and normally don't even care about. This one we often care about because it's that nice timestamp. It's an epoch value, the number of seconds elapsed since January 1st, 1970, but you can easily convert that into a point in time. So this is the point in time. And at this particular point in time, our flight, this flight number, and that's the tail number, which is like, the particular aircraft flying from Chicago to LAX. This is general information about the flight that doesn't change with each event. But this obviously does. The current latitude, longitude, altitude, speed, remaining minutes, remaining miles of the flight, and its arrival time, and whether it's complete. And this TTL, this is 30 days. That's expressed in seconds, so that's 30 days right there. So our last microservice is going to save this information into the permanent cold storage, so that we satisfy that last requirement. So I'm going to stop that now, and that's the flight telemetry generator. So let's get into our first microservice, those no-fly zone alerts. We need to track all our flights. We need to constantly monitor each flight's location. And we need to issue those alerts whenever a flight enters a no-fly zone. We'll do that by monitoring the change feed. We'll watch each telemetry document, and we'll run a spatial query. We have designated no-fly zones, so we'll be able to tell the moment a plane enters a no-fly zone. Let's see a demo. So let's look at the code first and then run it. So in the last two microservices that I showed you for the Acme Web Store, I had a single project with two functions in it. And it is true, and I showed you how isolated they are by virtue of each being an individual function and each having its own lease collection prefix. But the fact that they live in the same project, it does mean that if one fails to compile, then they both fail to compile, and that when you are deploying one, you are deploying the other. So it's, again, in an effort to maintain better isolation, you see Contoso Airlines has each microservice in its own project. There's one and only one Azure function in each one of these. But they look very similar to the ones I started showing you. Before long, you start seeing the same pattern over and over. And I'm talking about this pattern here, the Cosmos DB trigger attribute. Here I'm using constants, which is, of course, better practice, but you can see it's the location container, if you look at the IntelliSense, that I'm looking at. Okay, so, but there seems to be quite a bit going on here. And arguably there's too much going on here. Again, the real responsibility of this microservice is to detect that a plane has entered into a fly zone so that an alert can be generated, let's say. It doesn't, the burden of generating the alert doesn't necessarily have to fall on the microservice either. I mean, as well, rather. Excuse me. But this is a demo, so I'm sending the email from the microservice. But and so there's a bit of extra code here. Well, this part we need. We need our spatial class. That's a business logic that has the ability to run spatial queries, and you'll see a little code there in a moment. SendGrid, if you don't already know, it's a very super easy to use service on Azure that makes it really easy to send emails. You could also be using an SMTP client, but then you would need a host name and a username and a password and a port number and all that stuff. But here you just need the SendGrid API key. And again, environment.get environment. Remember again, that comes from the local settings. So this particular microservice has more than just that Cosmos DB connection string in there. In the case of our email function, yeah, we have that Cosmos DB connection string that we saw before, but we also have that SendGrid API key, which lets you send emails, and the email is going to come from this email to my Hotmail account, and that's it. But also take note of this local HTTP port, because if you want to run and debug multiple microservices together locally, and you do, this is what lets you isolate them when you're running locally, each one on a different port. So all of our other microservices, the other three, are running on ports 7072, 7073, and 7074, respectively, to make that possible. All right, so now, we're going to be watching the event. The events are coming in fast and furious, but we want to throttle our emails. Yeah, we need to send an email the moment a plane enters in a fly zone, but do you want to then send an email every 10 milliseconds for as long as that plane remains in the no-fly zone? I don't think so. So we're going to have this dictionary. We're going to be keying that by flight number. We're going to keep track of the last time we sent an email for a given flight, and that way we can control how often we send an email once a flight has remained in the no-fly zone. I already started pointing out about thread safety. All your code must be thread safe. There are many different ways that you can implement thread safety. I'm just going with a simple thread lock. There's other ways to do this, but inside I'm going to just jump down to the code that, you know, if you've worked with multi-threading before, you know that in between the time that you check for the presence of a key and the time that you actually add or update that key, you need to make sure that no other threads in parallel are running at the same time, and this thread lock lets you do that. But let's look at the logic, okay? At the top level, I'm checking the flight location. Right. So unlike the other microservices, I am not persisting any data. I'm not writing to another container in any way. I'm just watching each event. And if you're not in the no-fly zone, I'm letting the event fly by, no pun intended. Like, I'm not doing anything with the event. But otherwise, we need to process the event. So here's the document. This time, instead of deserializing it to dynamic, because like before, I didn't know whether it was going to be a category document or a tag document, so it had to be dynamic. Here, I know the schema of every document I'm getting. Okay, so that's that. Right. So and you know, .NET people love that strong typing, right? So we got strong. This is all within IntelliSense. I know it's strong typing. So are we in a no-fly zone? That's my spatial. That's my business logic in that spatial instance. So let's go. By the way, I want to. Okay, well, let's stay focused here. Is in no-fly zone. This is demo land, so this is hard coded. You know, you probably have a list of no-fly zones in the database. Each one would be more likely a some sort of polygon that you would run an intersection query against. Here, I'm just hard coding a distance query for the 150-mile radius around Washington, D.C. So we're saying you can't fly within a 150-mile radius of this latitude and longitude. So this, you know, I've got code that calculates the distance. That's not really interesting to look at. But, you know, if the distance is within the allowable radius, then you're in the no-fly zone, will return true, otherwise will return false. So if you're not in the no-fly zone, then I'm going to bail out. I'm basically just ignore the event. Otherwise, If it's the first time this flight is entering the no-fly zone, I want to send an email immediately. But otherwise, I only want to send an email a minute later, let's say, if if that same flight is still in the no-fly zone. So we tried to get that date, and if it's there for the flight and it's been less than, but it's still not a minute yet, then again, we'll just return to bail out and ignore the event. Otherwise, we either need to add or update it, because if it's the first time they're entering the no-fly zone, or you've been in there for more than a minute, and 2 minutes, and 3 minutes, and every subsequent minute we'll update the timestamp. But all that needs to go inside the thread lock to ensure thread safety. Otherwise, you could get multiple emails, or worse, get an exception with 2 threads trying to add the same key to the dictionary. And that would also throw an exception, although those would be bad things to happen, right? And this sends the email. So sending the email, again, maybe you wouldn't want the microservice to be doing all this work, but I'm formatting some nice HTML here. I'm formatting an HTML table row, a TR tag here to make the email look pretty. So exceptions could definitely be thrown out of there. And I'm getting my so let me go back up to these statics. We are relying on state. We're relying on this timestamps dictionary, like being there, if you will, right? But if you're using Azure Functions and your Azure function remains idle for too long, then remember it will shut down, and when it starts back up, you're going to lose all these statics. Obviously, now it won't be so terrible. I mean, well, first of all, it's not going to happen as long as your flights are in the air. Your function won't go idle. But it's just something to be aware of. So I'm relying on those being safe. But if the function does shut down and restart, then all of these all new up once more, and everything will be fine. So that's it. Let's run it. But I've also got some eye candy to show you. This desktop project. So I'm going to run multiple starter projects. I'm going to need my flight telemetry generator. Wait, I'm sorry, I should have cleared all this out. So the desktop project I want, the generator I want, these I'm going to all shut for now. Just the email alert. This is the one we're looking at now. We're going to start that along with the telemetry generator, along with my desktop app. Now the desktop app, and you can laugh at me if you must, but this is a WinForms application. This is Windows Forms, using the Bing Maps control for WPF, because there is WPF interoperability available in WinForms. I'm hoping that we get good performance here, because it seemed really slow before. So one of these is the Azure function. There's the telemetry generator, which we saw. This is the Azure function, which you get some nice ASCII art. I can already tell this is running way too slow. It would be great if we could check if anyone is on video. It would be great if they could kill the video. But here you can see some nice ASCII art showing up for the Azure function. Here is my Bing Maps display. I've got pins for all my airports. If I click on Washington, D.C., I get a little circle around the no-fly zone, so we'll be able to see when to expect emails. Now, if this thing is running ridiculously slow, I'm not going to want to hold things up. And it is running ridiculously slow, because it is only now just started, as you can see. Oh, wow. I guess I had state in the lease container. So it's actually from all the telemetry that I ran before. I should have emptied the lease container before starting. Okay, I think it's caught up. Oh, no. Let me start generating some flight telemetry. This should start waking up again. And it does. So it had just caught up. But every place where you saw yellow was my warning. And if I go to my inbox, let's see here. Yeah. It's 6:49. Great. So there you can see I'm, getting these emails. And here's the HTML formatted email. And there you can see at 6:49 p.m. today, 6:09. So this just came in. So there's your email alert microservice. Oh, there we go. Again, it's been a minute. 6:49 to 6:50. Now, let me now track the flight. Okay, I'm going to at least track a couple of flights. Let's say these two. These are the two westbound flights that were triggering the alerts. Right, going from JFK. Right. So now, how am I actually displaying this real-time flight map? I'm doing that by querying the location container, and that's what's making it possible. So let me put a stop to this, and actually stop the generator, shut things down, and move on now to querying real-time flight data, like what we were just looking at. And just do a quick time check, make sure I'm not going over. Wow, I'm over by 7 minutes, so okay, I'll try to make up for the time. Querying real-time flight data, as you can see, we can just run this query. We know what the documents look like. So if I know my flight number, I can order by that timestamp descending. And with the select top one, I'm going to get the most currently available data for that flight, right? And that's how I was actually displaying that information. So now I can present the live map like the one you just saw. And I didn't hover with the tooltip, but if you hover with the tooltip, you could see, get all the other information coming out of that most current document for that flight. So for every flight that I want to track, I need to run this top one query. So let's run that demo again. Okay. And just because things are running, seems to be running a little bit faster now. Okay, that's better. Hopefully, situation has improved. Good, that's good. So that's a little bit more like the speed you can expect. So let me start the gen. Let me get my planes in the air. See, that's a little better, I think, than what we were seeing before. So let's watch one flight. Let me maximize this out. Watch one flight. Go to logs. There's that select top one query I was talking about. Look at the cost. 47, nearly 48 RUs in some cases. Now, if you're not familiar with Cosmos DB, you say to yourself, is that a lot? Is that a little? I'm here to tell you that's a lot. And I only have 20 million documents, which is not a lot. And the cheapest you could expect this to be is 3 RUs if this was a completely empty container. And you see it just goes up. Think about it. I mean, that top one query is a cross-partition query, right? We don't know what partition it is, and we don't know the ID of any of these documents. They're all GUIDs. So this is ridiculously expensive. I would actually say prohibitively expensive. And you can see how the RUs are racking up. I mean, if I just go and change this and look at all flights, all 12 flights. Now we're watching all 12 flights, okay? And you can just see the RUs racking up at, I would say, at an alarming rate. I'm polling every 3 seconds, so I'm running this top one query every 3 seconds for every flight that you've selected. I'm already in the many thousands of RUs. So this is just bad. I can't think of any other way to put it other than to say this is just plain bad. And that's where materialized views come in to save the day. So what I'm going to do is stop things down there. And talk about materialized views. So this is very expensive. We are running these queries over a mountain of data. So what we're going to do instead is build a materialized view. That means a tiny container, because we only really care about, at most, 12 documents if there are 12 planes in the air at a time. We're never going to care about more than those 12 documents, but it's got to be the most recent one, right? So we'll create another container. We'll call it the current location container, which will be a very small container. It'll be a very small container and it'll be partitioned on type, so everything will fit in one logical partition, but we're going to set the ID to be the flight number. We'll replace that GUID with the known flight number. And that means we know the ID and the partition key of every document, making it extremely cheap by comparison. Let me show it to you in the demo. All I need to do is, well, first look at the code, look at the microservice, the current location microservice. I similarly want to throttle because I don't need to update the current location microservice 10 times per, 100 times per second per flight. Once every 3 seconds will be more than adequate. I mean, it'll be very expensive to do all those writes for every event, and needless. It's perfectly okay if we are, and it's a similar concept as we before, using a dictionary to keep track of the last time we processed an event for a given flight, using the thread lock to make it thread safe. Very similar type of logic to determine if we should skip the event. So we're going to skip the event if it's been less than 3 seconds. But we're never going to skip the event, even if it's been less than 3 seconds, if the telemetry document indicates the flight is complete. Why? Because this event occurs once and only once when the moment a plane lands, and it'll never occur again. And you mustn't miss it. So should skip will always return false in that case, even if it's less than 3 seconds and it's the last one. But otherwise, you'll see the logic is very, very simple. Inside update current location. Again, assuming that I'm not going to be skipping it, just take the GUID that's in that ID and replace it with the flight number, and then upsert the item to the current location container. This container variable here, I have set that to the current location container. I'm watching the location container, the one that's filling up with massive amounts of data, and I am going to be writing or upserting to the current location container. That's what this container variable is. So that's why the upsert is on that container. But the partition key is location. Every document has the same partition key value in it, called location. Now, I'm going to go on back on over to the demo. Let me stop them all. And I'm going to add that to run as another microservice. Oops, sorry, I didn't. Yeah, no, actually, that's right. So let's add on now that current location microservice we were just looking at, so that it also starts up. Control F5. Hopefully we get good perf now, or decent at least. In the interest of time, I'm going to not dig into the same level of code for the arrivals port, so I can show you all the microservices. But you see I've got 2 microservices running, each independently. One of them is running on port 7072, the other one's running on port 7071, like I was explaining before. That's in local settings JSON. And they have different lease container prefixes, so they're sharing the same lease container. I'll get my planes into the air. Let's see, both microservices wake up. You see the upserts to the current location container occurring only once every 3 seconds. Let's look at that query again for one flight, but this time I'll use the materialized view. Now let's look at the cost. What's this? 1 RU? Now that's cheap, and it doesn't get cheaper than that. How is this possible? Because we're doing a point read. We're not even doing a query. I said before the cheapest query is about 3 RUs, and I'm getting it down to 1 RU. How? Let's look at the code in the client, which is going to be down here in my repository, my flight repo. Before, when we weren't using the materialized view, we were running this select top 1 query here, order by timestamp descending, and that was the very expensive cross partition query, right? But now, given a flight number going against the current location container, I can do a direct read. So no iterator, no pages, you're just very conveniently handed the document in the resource property of the result. It just gives you the document. You just need to know the two things are the ID and the partition key, and the partition key is always location. Right, because it's partitioned on type, and the type is location in every document in this materialized view. And that's the flag. And it should never be more than 1 RU as long as your document doesn't exceed 1K. Then it can start going up. So this is like, okay, look at this 28 RUs. This is what you would call dirt cheap. Click on the second one. Sorry. Now it's 2 RUs every 3 seconds it's costing me. Okay, obviously this is now going to be 3 RUs every 3 seconds. So 6 RUs, 9 RUs, 12 RUs. So obviously if I do another flight and I do another point read, that's going to be 4 RUs every 3 seconds, but there does come a point of diminishing returns. Remember I said the cheapest query is about 3 RUs, and all of these flights are in a single logical partition. So in my code, I made it smart enough that if there's more than 3 flights selected, instead of 1 point read per flight, it's 1 query for all flights. And look at the costs. Instead of 4 RUs, which is what it would have been, I'm listing all 4 selected flights in the in clause. And the savings just go up. If I go to all 12 flights, the cost is just 5.29 RUs. The cost if I was doing 12 single point reads would be 12 RUs every 3 seconds, and now it's less than half of that. And this is a very small cost. I mean, if I need to make the case any better, I guess I can go back to location map and uncheck use materialized view, go back to those very expensive queries, and you know what, 570 in the first second. Okay, we're now, we're in thousands, and if this doesn't sell you on materialized views, then I don't know what else will. So that's the current location materialized view. Now, in the interest of time, I'm not going to dig into the code for the arrivals. We are nearing the end, so I'm just going to, I think you get the general idea. If I need, I need to, for each airport, I need to know what flights are landing and when they're landing. So I would need to group by airport, and I would need to get the most recent document, right? But I don't want to rely on the current location microservice. You don't want one microservice relying on another. So I still want to rely on just the location container, which is a gargantuan container. So to run these queries on every request and do the grouping to group the flights by an airport, that'll be very expensive. So instead we'll create a materialized view. What do I mean? We'll create another tiny container with documents that look like this. Like our microservice is going to produce documents that look like this. And then we can do a single point read on the ID. The type is arrival, always will be arrival. The ID is the arrival airport. There's an array of flights that are arriving and the remaining minutes. So it's very easy to display the arrivals board. I'm not going to dig into the code like I said, except to show you that the arrivals board microservice, which runs on port 7073, looks very similar. It's going to update the arrivals board only once every 5 seconds. But you'll see that there's grouping logic. I mean, I'm not going to go through the code, but there's the grouping logic in here that in this dictionary, this is the dictionary for those documents I just showed you on the slide that are going to go into the materialized view. The key is the airport. The value is the airport arrivals, which has inside of it that list of flights that are arriving at the airport and the remaining minutes. So that becomes a very cheap query than if we had to go against the location container itself. So time to close some of these things down. I'm still running my telemetry generator. Whoa. What the heck? Go away, go away, go away. Let me break out a full screen here so I can see if I have anything else running that needs to stop. So let's add the arrivals board microservice. But at this point, you hopefully are getting an appreciation of all these microservices running concurrently and independently and in isolation. So I go over to the arrivals board and start that one up too. Now they're all starting up except for the last one, the data archival one. And then I'll start them all up. And while we're waiting for them to start up, have a look at the least container inside this database. Now, this database has grown quite large. I actually have 2 physical partitions at this point with 20 million documents. So that's why I have 3 documents for each microservice. But each one's independently tracking. You can see I've got 4 microservices. Each of them is sharing the same lease container, maintaining its own independent set of bookmarks. So this is the email alert microservice. We'll minimize that. This is the current location microservice. We'll minimize that. This is the one we want to watch. It's it's catching up because the others were running and it wasn't. But I can now go over to my arrivals board container and pick an airport and see the flights that are arriving and when they're arriving. Now it has finally caught up because it went back to sleep. So let's get our flights back in the air. And now our materialized view, we will see updating. There's only 4 airports that we are arriving at, even though we have 6 airports in total. But this is a single point read, so I'll look at my log. 1 RU to find all the arrivals for JFK. If I want 2 airports, now I've got JFK and LAX. These are 2 documents because each document has an array of flights arriving at that airport. And now it's 2 RUs per 3 seconds. So there, it's the same concept. You create materialized views for anything and everything that you need. Let's stop the telemetry generator and then open our final microservice, and we'll be done with the presentation. And we know that every document is going to be deleted out of Cosmos DB every 30 days. So in order to satisfy our regulation for a permanent archival, we're going to have our final microservice called the data archival microservice that is running on port 7074. And in addition to the usual Cosmos connection string, I've got an Azure Blob storage account, the key to that account and the name of it. So that in the Azure function itself, which is the microservice, now I am not going to store one document in Azure Blob Storage for every event. That's not necessary. The mandate isn't that stringent. It's okay if I have if I can go back 10 years, and for any flight, within 15 seconds, I can tell you the altitude, latitude, longitude, and speed of the flight. That's adequate to satisfy the regulation. Otherwise, our blob storage container would also get out of hand, right? So, in our initializer, we just get, if you ever worked with blob storage, you know what these storage credentials are, and the cloud storage account is just a way to write to your Azure Blob Storage. It's the same location container. All our microservices are consuming the same change feed on the same container. So there's no dependency on one to the other, but they all have individual lease container prefixes for the same shared lease container. And in this case, create the blob container if it doesn't exist. It should skip. Remember, should skip means every 15 seconds. Refresh seconds is set to 15. But I don't want to miss, again, I don't want to miss is complete, even if it's less than 15 seconds. I want to permanently archive that in blob storage, even if it's within the 15-second interval. So that takes care of that. And here's the code. I just formulate a file name, get my blob reference, and this is just standard Azure Blob Storage code. There's the upload. Let's run it, and we'll be done. Remember, it's just another startup project, data archival. And I won't even have to start my generator because since I had a stateful lease container, this guy knows the last time it ran, and I've done so much flying. So this kind of shows you that if for some reason your email alert microservice wasn't running for whatever reason, does it mean you could miss that email? No. You won't get it at the moment the plane enters the zone because your service isn't running. Oh, what happened here? I must have not closed down the other 7071. It's okay. I just need, and same for 7072. I just need my, this is the arrival. This is the one. Yeah, there we go. You saw that yellow? I don't want to wait 15 seconds, so I'll just scroll up and show you. There you can see, right, archived. And interesting, it's 12 documents and a clip, actually, because there's 12 flights. But it split that across 2 threads, and it's 6 each. In other words, in one instance, this guy had 6 documents in it, and in the other instance, that changes array had the other 6 documents in it. But I did not have to write any parallelism code or any code to figure out that, hey, let me scale this out. That happened for free. So I'm looking at the time, it's 7:09. I think I'm pretty much on schedule. I was guessing around 90 minutes and started about 10 minutes into the start time. So with that, I want to thank you all for your attention and for your attendance. And particularly I want to thank Chris for facilitating the event for us. And definitely open up the floor to Q&A at this point, if you're up for it.
Cool. Does anyone have any questions?
I'm going to break my screen share.
You ever run into your bill on Azure because you're running all these tests?
Okay, so I had trouble hearing that.
Yeah, I think we had a bit of an echo there.
Yeah, I wonder why. Do you ever get an issue where you run into your Azure bill going up pretty high because you're doing a lot of these demos with this type of data?
Oh, you're talking about the cost. Well, I don't know if you. Well, I have an Azure MVP sponsorship, so I don't actually have to concern myself with it. But you should be aware that there is a free tier available. Okay, which costs nothing as long as you don't exceed a certain throughput. But if you want to exceed it, you can. Yeah, and there's also an auto scale mode. It was called autopilot while it was in preview, and that's definitely very much recommended when you're in dev. When you're in dev, you want to go with auto scale. So you pick an upper limit, and it will scale up to that and down to as little as 10% of that. So between 400 and 4,000, for example. Or between 1,000 and 10,000, for example, and that way, when your telemetry generator is running, it'll throttle up. But as soon as you stop it, it'll go down. As opposed to if you forget to lower the throughput and you go to bed at night and you're incurring all those costs, you want to go with autopilot. I'm sorry, auto scale. They only called it autopilot while it was in preview. It's called auto scale.
Thank you.
Sure.
And with Cosmos DB, is there any maintenance you have to do? Every time I've ever dealt with real-time data, large amounts of data like this, there's always maintenance things you got to do, but it seems as though they may have wrappered that, and it's just
sure. That's the whole point of the platform as a service, and they manage all of that. They manage the maintenance. There's really nothing for you to maintain. This thing is always up and always available. It's fully indexed.
That's great. Thank you.
Yeah, pleasure. All right.